So again, the obvious reminder that we do have the quiz today, which will become available about 2:10. And what I'm going to do to start is do one example that is something similar to what's going to be on the quiz, and then do it in two different ways. In other words, do a really quick rundown of how 4.2, 4.3, and 4.4 relate. They're all looking at the same thing, line integrals. They're just doing it in different ways. So let me start with the example as what you'll get on the quiz. So we have fairly basic force or vector field, and on this, this part, the way I'm going to do it is it's three different ways. So actually, we're going to do 4.2, 4.3, and 4.4. But first one I'll do 4.2, so I'll mention which section it comes from for each one. So the first part A will be 4.2, part B will be 4.3, and part C I'll introduce quickly 4.4. So A. So this is 4.2. Find, I'll call it the work. Just that'll make it easier to do it. So this is the quiz question. Here we have the vector field and we have a path. What are the steps to do this? So first little thing is, of course, we're going to split it into the two pieces. So we're going to do the path at C1 and then we're going to do the path for C2. So let's start with the C1. What are the steps to get the work to move along that path for this on this force field? First step is get the displacement vector because we're going to get the parameterization. So we know we're going from, if I call this A to B, then the displacement vector is just 2, 0. I can just read it off. And therefore I get xy is equal to, I'll go through the full thing, although here it's silly. So get the displacement vector, and then it's equal to the original vector plus t times the displacement vector, and that gives us that the parameterization is 2t, 0, and t goes from 0 to 1. So as I said, if you do it this way, it's always going to be 0 to 1. But for example, we could do that the displacement is vector is, parameterization is t0. The only difference is then we will go from 0 to 2, and we get the same thing. So for the lines, there are usually at least a few different pretty basic ones that you could use. So first step, parameterization, there it is. Second step, what do we do now? Right, so plug it into the force field. So put in x equals 2t, y equals 0. So I get 4t, 2t. Yes, so if you do it like I did here, which is get the displacement vector from the origin point to where we end up, and then do the origin point plus t times the displacement vector that we get, then it will always be t equals 0 to 1. If, as I said, so if I made it that our parameterization is t comma 0, then in that case, instead it would be 0 to 2. So if you do it the way I did it here, it's always for lines. It's always 0 to 1. But in general, it could be anything. It's just what parameterization you use. Okay, so I got plugged it into the force field. What else do I do? Right, so take the derivative of the parameterization. So the parameterization is 2t0, so therefore the derivative is 2 comma 0. And then finally, I put this into an integral, and we have the 0 to 1, so we have 0 to 1, and it's the integral of what? Right, so the dot product of these two vectors. And so in this case, you get 0 to 1, 8t. And even though obvious, that's pretty obvious, that's 4t squared, so it's 4, I'm going to leave it like that because this is what you should be showing on the quiz today. Write down your parameterization, plug it into the function, take the derivative of the parameterization, take the dot product. So this is what you should be getting to for the quiz. As usual, suppose this was 8t plus 16t. As usual, you don't have to simplify algebraically. So if it was 8t plus 16t, you could leave it like that. Just do all the preliminary things. Plug in, take the derivative, take the dot product. So since this is on a quiz, let me specifically ask any questions on this part, and then we'll do C2. So since it's here, let me ask what the parameterization is for C2, but then I'll do it on the next slide. And actually, why do I call this just so I have a label for it, A? So what is the parameterization for C2? I'm trying to save space, so I didn't specifically say, but that should be a circle, right? So 2 cosine, just whatever the R is, which here is 2. So I get that. And then we're going to do the exact same thing. So before I leave this again, let me ask one more time. Any questions on this before I do C2? Okay, so same steps. So let me put this back. I plug that into the vector field, which is 2x plus y, so 4 cosine t plus 2 sine t, and then x plus 2y, so 2 cosine t plus 4 sine t. And we take the derivative of the parameterization. I did forget to ask the one thing, which is what are the limits for t here? It's kind of knew what I was going to ask. So yeah, so t goes from 0 to pi over 2 because it's the quarter circle. And therefore, we're going to have the integral of 0 to pi over 2 of this that whole thing. And again, for the quiz, you're going to take the dot product, and this I'll not simplify, because again, for that, you don't have to simplify. So there it is. So as I said, you don't have to do any of the algebraic simplification. That would be fine, even though it should be pretty that this term and this term are going to cancel. So you can simplify if you want, but you do not have to. And let me call that B. And then what's our final answer? What's the last thing we have to do? We've gotten the line integral on them and add them up. So therefore our final answer will be whatever A is plus whatever B is. Right. So I'm going to give you something similar on the quiz, and you're going to pretty much write it up like this. So it's actually, even without doing the integral, it's a fairly long one. So any questions on this part? Yeah, so just somewhere write that, show that you know that you have to then at the end add up the two integrals. So you can label it like I did. I think on the review answer, I labeled one as integral of C1 and the other as integral of C2, and then said integral of C is equal to integral of C plus C1 plus C2. So just in some form, just show that you're adding them up. So the two types that you need to know for today are circles, and circles are just polar coordinates. The only thing here is, for this type of thing, we'll have a definite r. So instead of the general r cosine, r sine, we know r is 2, so we just put that in. And then for the first part, you just need to know how to get the equation of a line back from chapter 1. So the two types of things you need to be able to do are get the equation of the parameterization for a line, like the first part, and for a circle. Anything else I would give you the parameterization for, at least for today. Any other questions on this? Okay. So part B, let me rewrite this. Let's go back to now to 4.3, which we started quickly yesterday. And let me ask, is this conservative? Yes. And the way you check is that the derivative of p with respect to y is 1. That's equal to the derivative of q with respect to x. Therefore, it's true. Therefore, let's find f, the potential function. So we know that f is equal to the integral of p with respect to so I'm going to take the antiderivative of p with respect to which variable? Right. Because it's conservative, if this is the gradient of a function, which means the first term is the derivative with respect to x, the second is derivative with respect to y. So I take the antiderivative with respect to x, where I might be missing y's. And I also take the antiderivative of q, but now with respect to y. And then we put it together. Any term that's mentioned, and then plus the generic c. Just don't, this one's mentioned twice, don't write it twice. And now let's go back to the beginning. Here was our path. If it's conservative, what do I do? So I take the equivalent of the antiderivative, which is the little f that we just got, and then plug in the 2 points. And whatever that number is. It's actually, I might as well do it because it's easy. It's 4. If it's not conservative, then the path can matter, or actually it will matter. I didn't write down the theorem, but it is equivalent. If it's conservative, then the path doesn't matter. So this isn't on the quiz. This is section 4.3, but any questions on this? Okay, one more way. This way, that way has ended up being the easiest one. Right, so it's a different way to solve the same thing. And 4.4 will be a different way. So 4.2, 3, and 4.4 are all looking at line integrals. 4.2 is the basic way of doing it. 4.3 is, well, it simplifies if it's conservative, so it's a second way of doing it. And 4.4 is yet a third way. So I'm going to do the short version of the Green's theorem, which is, as usual, it has to be fairly nice, but if we have a closed curve, so here's the short version of the theorem. If we have a closed curve that bounds a region R, then for f is equal to PQ, the usual line integral over C is equal to the double integral over the region R of the two-dimensional curl. So let's go back to the picture. So C, we still have f of xy is equal to 2x plus y, x plus 2y. And I'm looking at this path again. So this is not closed, but let me make it we add a curve 3 that is now closed. Then what Green's theorem says is that the integral of C, so the line integral, is equal to this is R, the double integral over the region. And so this now goes back to just the double integrals we have, which is we want to integrate a function over a region, and so we do it kind of in the usual way. So I'll set it up, which is here's the region we want. This is x squared plus y is equal to 4. And so x goes from 0 to 2. The reason I'm not going to change it to polar coordinates, you'll see in a second, or you'll tell me in a second. And then 0 to 4 minus x squared dy dx. And given the last part, what is the function we're integrating? What is qx minus py? 0, because it's conservative. And so therefore, the integral for the full closed path is 0, which means now to actually get what we want, c1 plus c2, we get c3 and then subtract it from 0. So let's at least start it, because this is, again, a quiz question. C3. What is a parameterization for C3? Right, so again, get the displacement, which is 0, negative 2. So not quite that. So the displacement vector, so we're starting at 0, 2, and then t times the displacement vector, which is 0, negative 2. So therefore, r of t is equal to 0, 2 minus 2t. Oh, because Green's theorem says that the line integral is equal to this. And we found in the last part that qx and py are both 1. So we found this was 1, and we found this was 1 in the last part. And then we, from here, do the usual thing. Right? So I'm not going to do it, but we would plug that f and take the derivative of r and do the integral of dot product. And then once we get that, we subtract that from the 0 to get what c1 plus c2 is. So here, obviously, the second method of these three is the easiest. But let me do one quick other one of these to show that this method does work. So the first thing we would do is, because it's closed, conservative is especially good because we know if it's closed, the integral of the line integral will be 0. So is this, so let's actually look at what is, and let me label again, p and q. Let's do q of x minus p of y. So derivative of q with respect to x is 3, and derivative of p with respect to y is 1, so that's 2. Notice that's not 0, so it's not conservative. So therefore, the integral won't be 0. But that's nice. So instead of doing the traces using the method from 4.2, I can use the fact that the line integral on c is equal to the double integral on R of this. And then I can do it the usual way. But here it's even nicer than the last one. Not really. The last one was 0, so not nicer. But if I integrate a constant over a region, what does it give me? And let me make it more specific. I can take out the 2. If I integrate 1 over a region, what do I get? Right, so I get the area. So therefore, this is equal to 2 times the area, which means I don't really need to do the integral because this is just a triangle. Which I know. Right, just the length times the height divided by 2. So for things like this, where q of x minus p of y is simple, Green's theorem is really nice because we don't have to do an integral at all. Which means it's fairly typical to do things like this, where if you tried it the direct way, it'd be a pain because we'd be doing things like having e to the x times e to the t times sine of t type thing, and we don't really want to do that. So doing it directly works, it would just be a pain, whereas doing it with Green's theorem is pretty easy. Right, so this always works. It's just that if it's closed and conservative, the integral is always 0. So in some ways, getting this, you're checking to see if it's conservative. So if we got that this was 0, we'd be done because the integral will be 0. Because it's equal to the potential function at the difference of the potential function at the 2 points, but the 2 points are the same. So we don't even have to get the potential function. Oh, here. So this is, so Green's theorem says that the line integral is equal to the double integral over the region, if C is closed, of q of x minus p of y. And we got that here. So those are very quickly 4.2, 4.3, and 4.4. So 4.2 is, again, the basic way of how you do it. It always works. 4.3 is talking about conservative functions, in which case you can do it in a simpler way, which is take the equivalent of the antiderivative and then just plug in the 2 endpoints. You don't care about the path at all. And 4.4, Green's theorem says if it's a closed path, you can make it into a double integral of q of x minus p of y. So the area isn't 2. Because I can pull the 2 out, it's 2 times the integral of 1, and the integral of 1 gives the area of the region. And this is a triangle with a length of 3 and a height of 3. And we know the area of a triangle is 1/2 base times height. So this is the area. The 2 comes from the q of x minus p of y. So here's, let me write it down again. So here's Green's theorem again. This is what I did. In this particular case, q of minus p of y is 2. So this is Green's theorem. Obviously, we have to do examples. So Monday we'll be doing more examples from 4.3 and 4.4. Okay, so any other questions on this? Okay, so all right, so remind me on Monday. I'll look at 18. Sorry, I've now done it twice. So I will start with 18 on Monday. Right. But let me stop recording